Our speaker now is Xuanyi, and I nearly got it right. He's ex-Brisbane, but he lives in the big smoke down in Sydney. And he's going to give you a talk on monads in my Python. Okay.
Right, so I'm basically going to talk about monads, and because this session's before lunch, and I know everyone's sort of hungry, so I'll make this quite quick. Basically, what I'm going to talk about is what monads are, why you shouldn't be afraid of them, and some monads you probably already use. So let's cut to the chase. What are monads? Monads are just monoids in the category of endofunctors. No problems, right? Here's an example monad that you've been using so far. You've probably been using this, and that's it. The end. All right. So anyway, that was a joke, and probably the last joke since I'm not a very good comedian. Let's look at some real-life code. This is a piece of code that I wrote. Basically, it detects anomalies in time series, and I spent 2 months trying to port R's STL over, but that's a totally separate story. So anyway, I'd like you to observe some things about these code, right? The nature of code. The first thing that I'd like you to note is that, I'm not sure if you can see, you can actually see the mouse. Excellent. That I check for things, whether the obs per period parameter exists. If it doesn't exist, we'll raise an exception, right? A second thing I'd like you to note is that there is a somewhat sequential flow nature of the code. You first seasonally decompose it, and then you take the data, you minus the decomposed data, and so on and so forth, right? And the third thing to observe is that each line of code has references to previous lines of code in terms of its variables. Now, this is how I believe most real-life code looks like. As more so, especially if you're trying to expose the APIs of your package or your modules. So this is basically composition. If we say that X is the result of calling foo, and y is a result of calling bar with passing in X, and Z is passing in Y, it's a composition. It's basically this. Yes, follow? Yeah. Okay. Same thing for operators. If you say 1 plus 2 plus 3, it's equivalent to having an add function that adds 1 plus 2, and then take the result and add it to 3. And if you follow the math equation on the other end, you realize that you just divide it by 0 and the universe implodes. So while the universe is actually recomposing itself, let's get reacquainted with the notion of functions. We all know what functions are. You first define a function, foo, takes in maybe a parameter, maybe more parameters than 1, and then you do something with it. You either use the parameters or you don't, right? And now, we'll have a sort of side note into the annals of history. We'll note that before C won out and became the sort of dominant paradigm, Pascal had a differentiated notion of what functions are. Basically, Pascal differentiated procedures and functions, where procedures are sort of instructions that say you do this, and then you do that, and then you do that. Basically, Pascal procedures and even SQL procedures do not have return values. It doesn't return anything, whereas functions did. Okay? Now, there's a second notion of function that I would like to explore, and that's also the mathematician's definition of functions, which we can call pure functions. Basically, a pure function is a direct mapping from one value to the next value. It's a one-to-one mapping, and it's always going to be constant. So if you pass in, let's say, a number 1 into the function, and it has to return something that is always the same. Let's say the function is plus 1. So if you pass in 1, it becomes 2. If you have a function that says, okay, if you pass in 1 and depend on whether the moon is blue like last night, it may return 0 or something else. It returns some other value. In fact, basically mapping from one value into multiple values. That's not a pure function. Okay? So we can sort of graphically represent functions like this. You may have seen these in your math textbooks. And we can write the function like this, and that's valid Python 3.5, by the way, like this. Okay? This is contrary to what we know as functions. We have functions that may return a value or not. Now in Python, it's interesting because if you omit the return statement, it actually returns a none. All right? And the return values are not mapped one-to-one. So like I said, the once in a blue moon kind of functions. And most importantly, our functions are also sort of combinations of procedures that's in sequential instructions to do things. So we have this, and why are we interested in pure functions, right? Am I trying to convert you guys into being Haskellers? No, actually no. The reason is because that pure functions and what we call functions have some sort of similarity, and this is a starting point to designing better programs. So this is the comparison of what we know as functions and pure functions. Both take parameters, and pure functions only take one parameter. Both return values, and the most important part is both types of functions are composable. Now, mathematicians have noticed that from group theory, from ring theory, from metric spaces, from topological spaces, that there are things that can be composed and they kind of look like functions, but they don't necessarily conform to the idea of pure functions. So they came up with a new category of mathematics, and they call it category theory. So, what is a category? It's quite simple, really. A category is basically a collection of things. You can think of them as sets of values, okay? Like all your variables, or all the possible permissible values of a type. Arrows. You should think of arrows as functions, and arrows basically have domains, the inputs, and they have outputs. They can be composed, and they obey some form of associativeness law. Now, if this is you spaced out a bit too much so far, it's basically pretty pictures to help you think about composing stuff and functions. This is the typical diagram of how a category looks like. It says F maps X to Y, G maps Y to Z, and if this happens, there has to be a composition from X to Z, which is G.F. All right? Now, this is quite abstract, and it doesn't actually help us visualize what's happening. So I've basically changed that a bit and do it in the other form. It's the same thing. I've omitted the identity arrows because they're not very helpful for this visualization. So F is +1, G is +1. If you map value of 1 plus 1, it becomes 2, and plus 1 becomes 3, right? So categories are kind of cool, but what's the big deal? Why do we bother with category theory? Well, because category theory is the correct intuition to think about abstracting and composing things. When you want to abstract things out and compose things, you generally need to think about inputs, outputs, and stuff like that. And category theory gives us the direction to go. More importantly, category theory also gives us the tools to basically reason about the issues that we face all the time as programmers. I'm going to introduce 4 issues known as the awkward squad. Sorry, Simon Peyton Jones. He noted that I/O, concurrency, exception, and foreign function interfaces are basically issues with Haskell, right? But it's not only Haskellers who face this problem. We too face this problem. I/O is a problem because there's permanent side effects, and later I'm going to show you how to make a simple print hello world fail. That's fun. Concurrency, we all know about threads and locks and how messy it can be, and yeah. So in Python, we deal with exceptions quite easily. We've got try excepts, fair enough, and dependence on external information. Earlier, Hockey basically covered a lot of my points in my talk, so I'm just going to skip past them. So the thing is, due to all these external effects and side effects and, non-determinism, errors, or different types, our programs fail constantly. In fact, as programmers, we deal with failures all the time. Here's how you fail print. So you have a program that says, well, true, you print hello world. That's not going to fail, right? Unless you pipe it to head. Who doesn't know what head does? All right, head is basically a Unix program that takes an input, and it takes the top n lines that you pass it in. So in this case, the input, because we pipe it through, the input is basically standard out, and the output from the Python program we have is basically, it pipes it to standard out. So it reads from standard out, and then it closes the pipe. So when you close the pipe, your Python program fails. Now, I want you to think about how you would recover from this in a program. Failure scenarios are actually very, very common. And in fact, a lot of programming languages provide an opinion on what to do with failures. But so maybe we should delve in a bit deeper to see how we deal with failures, right? Now, here is a concrete example. We have division. That takes a numerator and a denominator, and then it divides. And a square root basically calls an external library, math, and calls function square root. This is a very simple example, but I want you to think of this as designing an API for your package or module. So when you design APIs, and you think of what are the possible inputs and what are the possible outputs from your methods. So let's look at that. The inputs for div and square root are basically any kind of numeric type. Yes? Everyone can see that? And what are the outputs? They are generally floats, because after you divide, it always comes out as a float. After you square it always comes out as a float. Fair enough. So let's try to put this in the context of category theory and see what happens. So you have a set of values, 2, 4, 5, 0. You pass it in, and let's make the numerator 100. And you pass in div, and you divide 100 by 2, you get 50. 100 by 4, you get 25. 100 divided by 5, you get 20. And 100 divided by 0, you get a zero division error. What is a zero division error? There is no defined, it's not defined as an integer, it's not defined, it's just an error. Then, because of this, the composition to square root becomes, the next step in the pipeline basically fails as well. So, okay, we'll say, right, we'll extend the range. We'll extend it from an error into some sort of known types. So we extend the range and say clean div is now either returns a float or a none. And we can do the same for square root, because square roots of negative numbers are basically imaginary numbers, and we're not going to deal with them now. So here I listed both ways that Python people always use to handle exceptions. One is a try except, one is an if check. The new ranges are basically this, float or none type. But the problem with this is once you extend your ranges, you have issues with composability. You cannot compose your functions nicely. You have to do an external check, right? You guys follow so far? Yeah. Cool. So the other solution would be to extend both the domain and the ranges. So you have input checks. You check for your inputs in your new functions, and basically you check that x is definitely not x is bigger than 0, or it's not none. The check for square root is interesting because you cannot do if not x, because square root of 0 is 0 and it is a valid value, right? So when we extend the ranges and the domains, it looks something like this. So you've got two types of valid input, and it passes in, right? And this is clearly quite tedious. To compose functions, you basically need to create new function. What's the point? Or you can do it like what we normally do, and this we do try excepts all the time. But the problem with this is it hampers on your readability and understandability and how you reason about your program. So the question is this: is there a way to generalize and basically map from this category into this category? Well, the answer is monads, which I would like you to recall that monads are just a monoid in the category of endofunctors. So let's have a look at what a definition of a functor is. A functor is basically a mapping between categories. Ta-da! You have just invented monads. So let's ignore what a monoid is. It's basically an algebraic structure with a blah, blah, blah. So a lot of theoretical stuff, right? I'm not particularly working at category theory. So let's talk about real life. Let's see how we can implement monads in Python. But before that, let's have a recap on what interfaces are. If you guys have been to Hockey's talk earlier, you probably already know what interfaces are. So we say that we create a new class called value and value no iter. And one of them allows you to use the for I in v statement. The other one doesn't allow you. The other one will basically say, hey, it's a type array. It's not an iterable. Right? Python doesn't have explicit interfaces like Java. It's sort of an I understand, you understand, we'll just sort of implement it kind of thing, unofficial, I guess. So in order to implement an iterable interface, you basically implement a dunder-iter method. Following so far? So that's how you implement monads in Python, or in any other languages actually. Monads are basically an interface with bind and unit. That's it. That's what monads are. Binds are basically takes two parameters, one's a function and one's the value, one's a monadic value, and applies the function on the monadic value. Unit basically creates a monadic value. Okay? And when I say bind and unit, it doesn't mean they have to be methods of a class. It can be functions outside of methods. All right? Anything bind and unit works on is a monadic value. And practically speaking, there are as many monads as you can think about. And this is something that a lot of people don't seem to get or get confused with, is that monads are like a design pattern, really. Okay? They're really generalized descriptions of computation. And the bind function, the bind method is basically you defining how your functions can compose with each other. Okay? So you may be asking, and obviously there's also the monad laws that apply, but I'm going to skip through this unless we've got time. So you may be asking, what are monadic values? You've seen them already, actually. This was the mapped out chart earlier. Let's box them up. There you go, monadic values. Basically values in a box with a context. The bind method simply makes the function f and g aware of the context that it is operating in. That's all. And what we've just did was basically design something called a maybe monad. Okay, the maybe monad deals with failure conditions. It applies a function if the input is none. If the input is not none. If the input is none, if the value inside the monadic value is none, we'll just say, okay, fine, it's none. And unit returns the value. Now, it's quite hard to talk about monads without talking about types, but fortunately in Python we can create our own types, and they're called classes. So we create a value class, which we'll see later, but here's the bind and the unit. So the bind basically says that if it's not none, or if there's a none in the keyword, we'll just return none, and we'll apply the function to the value. I have a helper function that unboxes the value, which takes out the value so that the functions can actually apply on them. And another thing is that I wrote this in the form of decorators, because this is how I use them. Really, the maybe monad is so simple that there is no need for an external library. You just write your own decorators. And this is the class. In fact, you don't even have to write a class for the maybe monad. I'm just wrapping it in a class to make sure that you're aware that what unit does. So, follow so far? Cool. Here's how you implement it. You say, look how nice the div and the square root functions are. It's basic checks. That's all. There's nothing funny happening. And when you apply div 100 to 4 and then square root, it just comes out with 5. And the type is a value, the class value, right? Maybe we should try tanking the project. And we say divide 100 by 0. Now, because it's a monadic value, it knows that it returns none. It returns none here. So when square root is applied to none, it knows that the bind knows that, okay, we're just going to short circuit this and return none as well. Okay? So bind basically applies the function onto the monad, and the unit basically makes sure that the return function is a monadic value. Now, I'm also going to talk about the next monad, which is, also that you can nicely chain them up and nothing's going to sort of freak out on you. The next monad we're going to talk about is the list monad. The list monad basically applies a function inside a list and flattens the result if the result comes out as a list. The unit is very simple. It puts the element in the list. Simple. I didn't write it as a decorator this time. This is just to push home the point that monads can exist in a variety of forms. Okay? And you're going to see a different form again later. This list comprehension is a bit hard to understand, so it's basically for I in X, we apply Fi, and then Fi will return a list. Then we'll just flatten it out. We'll take each element of a list and put it back in the list. Unit is simple, it just returns it in the list. And we'll define a new function called square root this time, and we all know that real numbers have two roots, a positive and a negative root, yes? So if it's less than 0, we'll return an empty list because there is nothing to be square rooting. But if it's not, we'll return two values, the positive root and the negative root. So this is how you apply it. If you apply bind on apply square root to a unit of 100, basically a list of 100, it returns 10 and negative 10. Now, and then you can chain them up nicely, and it only returns 2 because it doesn't do, when it iterates through an empty list, it doesn't return any values. Following so far? Cool. Or you can just, pass in bind square root on a list of numbers, and it'll return the numbers correctly. Now, if this seems a bit familiar, it's because you've already been using it. List comprehension is a kind of monad. All right? And you can, again, do it in list comprehension, or you can apply map on a list. Obviously, these will not return the same result as these. These two functions will return list and list. Yes? Was that a question? Oh, okay. So let's see what's the general idea. The general idea is that monads help us with composition, composing functions with different return types. And how you do it is basically you wrap something in a monadic value, which you can define on your own. It can be a list, it can be a class, it can be two separate ideas. All right? And then you define a bind which explains how to compose these functions. That's it. Now, before time's up, we'll look at one last monad. And it doesn't have a name, but we'll just look at it. So we define unit as return the open file and then call the dunder-enter method. And the bind is written as a decorator on a function that applies a function onto the monadic value f. Okay? Monadic value x. And then after that, it calls the dunder exit and then returns the return value. And we'll say do stuff is read lines. And we'll call lines do stuff. Does this sound familiar to you? No? This is basically a monad. And remember that monads basically allow you to apply a function within a context. What is this called? This is called a context manager. Hey, Python's provided you monads. Now, in reality, though, a lot of monads exist in Haskell, and we don't need them because Python provides extra shortcuts for them. And we can handle short print statements and side effects without much of a problem. So the idea is that we want to be aware of what monads are. Okay? Here are some other possible monads. Twisted's deferred is a monad, and it was written 10 years before it promises, just so you know. Django's query and dot filter are also monads. The results of those are also monads. And I have to actually check if those are actually monads. But anyway. After all this, why does this all matter? Okay? Because programming is all about composition. Composition is the heart of programming. I started this talk with a function that shows you that it's a sequential manner. You use previously known variables and stuff like that. It's basically composition, all right? And I think that programs should be easy for people to reason about. Instead of haphazardly recreating solutions, why not have a general solution and apply it to the underlying problem, okay? Nicely composed functions also allow us to think about programs in different paradigms, basically. If you like, anyone here uses D? No, okay. Anyway, there's this really cool thing where D has a thing called UFCS, Universal Function Declaration Syntax something. Syntax, yes. Basically, you can at any point in time you can chain a function in D. If you like the UFCS, why not apply it in Python? And if you apply it, if you create that paradigm in Python, it's most likely going to be a monad. That's it, really, the end. Questions?
Righto, if you've got any questions, come on up to the mic and ask him.
Did I lose you guys somewhere in the category?
There we are. Yeah.
Could you just put that last slide back up?
This.
Awesome, yeah. So looking at it, so what you're talking about here, I guess, is really quite interesting in your explanation of monads. I'm somebody that loves the theory of functional programming, but it's not a functional programmer. And monads are that really hard thing that it kind of like assist growing in your head and you're waiting for it to explode. So I enjoy what you've done because you've kind of drawn some patterns around that. But I want to know, as an engineer, how is that helping you attack your problems? Because what you're saying on this last slide here is, to me, I'm reading it as you're finding that you're creating more...
Abstractions?
Well, I was going to say abstractions. Maybe that's what you tell me then, if you think you're creating more abstractions. What do you think you're doing with this? Like, how is that actually, I guess, say word it better. How is this making you a better engineer, and how do you think this is making you write more optimized code?
Optimized, I'm not so sure about optimized, but it's I can write code that I can reason about better. If you look back into the first slide I had, you'll see that the checks are only in the top part of the function.
Yep.
After that, I don't check with anything because everything.
Okay.
Then, if you look at a code like that, I can reason, hey, I'm doing this, and then this, and then this, and then this. It makes it easier to reason about the code. Now, clearly, you can write some really optimized monad, but I just use a simple maybe.
All right, so what you're doing with it then is, because obviously you're talking about this as applied to Python, but then you also spoke about applying things, other ways you can apply it in other languages, etc. So really what you're doing with this is using it as a design pattern for how you're approaching your problems.
Correct.
And you find that design pattern you can apply, because it seems to me the way you've done it there, I could pretty much apply that across any language I wanted to.
Yes.
Yep.
That's actually true.
If you're...
Some languages are harder than...
Ask a question, or...
It's more difficult to apply this in some languages like Java because they don't have first-class functions.
So Java, or have you done it with JavaScript stuff as well?
I have.
Yeah, so you find JavaScript is easier to apply it to than Java?
Well, it's easier to apply anything to JavaScript than Java. So. Java is just classes all the way down,
So, and one last really quick thing. When you're mentoring junior developers and engineers, how do you find that this is a great way to get them... Because, the hardest thing is to actually get them thinking in design patterns, right? And not just slapping up code. So do you think that this is a good way to approach that problem?
I don't do a lot of mentoring, but what I think of this is basically creating a language on top of language, and then people just apply the language, the new language to write code.
Cool, thank you.
Sorry.
Yeah, thanks for an awesome
Luke.
talk. It was great.
Lachlan, sorry, Lachlan.
I suppose the first comment I'd make is that I echo your view on it. I find it really useful for data manipulation and pipelines.
Yep.
So I think I really appreciate that, and I've found that it's actually the functional methodology is actually quite good for that. My question is actually how you're finding performance of applying this on top of Python, because there's arguments like the Haskell performance issues and open question, and I wondered if you have you had any feeling on how this performs sitting on top of a language that isn't inherently functional?
Well, performance-wise, I've not had any complaints, I guess. So I've not looked into optimizing it. I mean, there is a library called PyMonads that's probably more optimized than my not invented here syndrome things that I keep doing. But yeah, what I do is I don't do a lot of recursion. Like functional programming, you think a lot in recursion, but I don't do a lot of recursion, so I don't run a lot into Stack Overflow issues and stuff like that.
Cool. And are you going to put the slides up somewhere online?
Oh yeah.
Yes, they're all. Cool. Awesome. Thank you again.
Are there any more questions? We can still take another question if you need it.
Quick question. Did I lose you guys somewhere? Just checking. Thank you.
So the problem that I occasionally have with functional programming is that when you get to the highly abstract level of functions, to make it sort of efficient and clean, you lose the narrative that somebody talking to you about their problem. They go, so I want it to do this, and then when they make this decision, I want it to do that, and then I want it to do, and they tell you a story.
Yep.
And then when you go, okay, now I'm going to think about this in a functional way, most efficient way is you go, so I'm taking something, and it doesn't match that story. Do you have any ways of making that map easier for yourself?
Yeah. I've not actually talked about this in a functional way. If you
and you haven't, and so that's been really
So generally is the thing is you can the idea is that you wrap things in a context and you talk about them in that context.
Yeah. Okay.
So if you can design a sort of meta language like a DSL or something like that to describe the problem, like a lot of people actually use monads to create chains of functions. So it's easy to read, so you apply this and then you apply this and you apply this to one value.
Yeah, cool.
So that's how I would think about following the user story, I guess.
Okay, thanks very much.
Does that make sense to you? Cool.
Righto. Well, Xuanyi, this time the PyCon committee decided to give you an Aztec blood mug, and you can only use this. It's a unique piece of ceramics here, and you're going to use this to drink green tea from. It will explode if you put coffee in. Thank you very much. Put your hands together with Xuanyi Chu.